Hello.
Hello.
Hello, dear participants. Welcome to Fifth International Congress on Human-Computer Interaction, Optimization and Robotic Application. The symposium organized by Tokat Gazi Osman Pasha University from Turkey and National Technical University Kharkiv Polytechnic Institute from Ukraine. The symposium is also technically sponsored by IEEE Turkey section. Thank you for your scientific contribution and support to the symposium. Okay. If you are ready, we can start the presentation and session. Dear Boris Kostov, are you ready to present?
Yes, I'm ready.
Okay. You can start your presentation.
Okay, I'm sharing my screen. 1 second. Can you see my screen?
Yes.
Okay, I'm starting with the presentation. Hello to everybody from me. My name is Boris Kostov. I'm from Sofia,
Please, you
Bulgaria.
have 10 minutes.
Okay, I will present today my presentation, which is on with the name Optimizing Cycle Time of Industrial Robot for Loading Molding Machine. This is a comprehensive analysis and optimizations approach. As the introduction, in the paper which I have written, I have measured the cycle time of industrial robot, which is already implemented in real cell, working in real environment in a real factory. The robot is a Mitsubishi robot, 2 kilos payload, 6-axis robot. The robot is equipped with Schunk grippers, 2 fingers parallel grippers. And the main problem is the slowest cycle time. In the paper, I see, I check that the industrial automation process and the optimization of the cycle time of the robot system is very, very important for the manufacturer to can be competitive on the market. It doesn't matter in which sphere, on which market is the manufacturer working. Here, briefly, I will introduce to you the system, which is, as I said, already implemented. The system is a closed cage, and it contains a vibro ball, which you can see here. In the vibro balls are the parts which after that are placed in the molding machine. From the vibro ball, the parts are passing through a thermotunnel where they're heated to 90 degrees Celsius. After that, the parts are going on one servo revolver from which the robot is taking the part. After that, the robot is placing the part 3 by 3 on the instrument, which you can see here on the 3D model, where is the green table. The whole amount of the parts which can be placed on this molding machine is 12 parts per side. The robot is placing 4 times per 3 parts. After placing all 12 connectors, the molding machine is rotated, and if there are already molded connectors inside the machine, they go in front of the robot. The robot is cutting the runners of from the silicone, taking the plastic parts and placing them on a conveyor belt, where they go on a special inspection for the silicone. The whole processes was at the beginning around 41.1 seconds. Here in the table, you can see for every one of the processes, for every one of the steps, what was the measured cycle time before implementing the optimizations. As you can see, the slowest thing were picking both of the connectors and waiting the signals from the machine, the signals from machine cannot be optimized very good because it depends on communication Euromap protocol. Here on this slide, I briefly introduce what are the implemented optimizations and how the cycle time is reduced. You can see in the table the reduced cycle time, and on the graphs on figure 4, you can see the differences between the cycle times before and after optimizations in the seconds. And on the figure 5, you can see graph comparison between the cycle times before and after optimization. The optimization which have been done can be briefly categorized on 4 different categories. One is positioning improvement. In the positioning improvement, the accuracy of the robot was taken in place, and it was getting better and better, the accuracy of the robot. On the second, it's movement optimizations. Unnecessary retracting from the points were shortened. Also, the path of the robot was optimized by adding new points, moving the old points, deleting points. The third optimization is the signal processing, which, as I told, it cannot be optimized as much as I want because of the restriction from the protocol used to communicate with the modeling machine. And the third process was the system optimization based on measurements. This was the slowest as taken in time optimization, because a lot of measurements during the weeks, the months were taken, and some optimization were managed to be placed. One of the optimization is the cutting tool for the runners was changed with brand new, which reduced the cycle time because optimized the cutting and the throwing of the runners. And as a conclusion, I can say that the cycle time was significantly reduced. The manufacturer in which site is installed the system is very happy and of the cycle time, and the cycle time, the final cycle time cover its wishes. And the manufacturer will proceed with 6 new stations like that, on which further optimizations will be placed. Thank you for attention, and I'm waiting for your questions.
Okay, thanks for your presentation. Dave Parsim, do you have any question about this presentation? Okay, no question. Thank you again. I wish you success in your career, dear Boris Kostov.
Okay, thank you very much.
Thank you. Dear Edward Soli.
Hello, yes, I'm here.
Okay, are you ready to present?
Yes, let me
You
just
can start if you want.
Okay. Can you see the screen?
Yes.
Okay. Hello, my name is Edward Solly, and I'm a master's student, and today I will present the gesture-controlled mobile robot. This work is sponsored by the Electrical and Electronic Engineering Department of the University of Nottingham.
Sorry, you have 10 minutes, please.
Okay. Gesture-controlled robotics is the use of human movements which translate to robotic actions. This research project specializes the use of hand gestures by developing finger tracking and motion tracking systems which are implemented onto glove controllers. The purpose of this is to expand the human-robot interaction principles by developing gesture control technology that has applications in a wide range of industries. The most relevant industrial application is the pick and place task in manufacturing. Gesture-controlled robotics presents several challenges that can affect the practicality and widespread adoption in industry. While the idea of controlling robots with gestures is appealing, there are certain limitations that make standard control methods more preferred in many industrial applications. Two significant challenges in gesture-controlled robotics are the lack of high precision in detecting gesture actions and the latency experienced in response times. Even with advancements in sensor technologies like wearable devices, there can still be inaccuracies in gesture recognition. Small errors in detecting gestures can lead to unintended robotic movements, which can be problematic, especially in safety-critical applications. Achieving a consistently high level of precision in gesture detection is a challenging task. Another significant challenge in gesture-controlled robotics is the latency experienced in robots' response to detected gestures. Gesture recognition algorithms need to process the captured data, analyze it, and translate it into appropriate commands for the robot to execute. This processing time can introduce delays between the execution of the user's gesture and the robot's response, impacting real-time interaction and potentially causing frustration for the user. The aims of the research project were to create and enhance two glove controllers that can remotely manipulate an industrial-style 5-axis robotic manipulator and a robot vehicle using hand gestures. As well as this, the research project aims to further advance the field of human-robot interaction principles and to expand the potential aptitude for industrial applications. The design process involved several stages. For the robotic manipulator, it was important to gather information about existing robotic manipulators in industry, including their functionality and design principles. It was then necessary to define the specifications and requirements such as size, weight, range of motion, and the performance criteria. The robotic manipulator presented has a gripper end effector, which is commonly used for pick and place tasks in the manufacturing industry. Following this, the electronic circuit was constructed and the overall robotic manipulator was assembled. The last stage in the design process was to write the code to operate the robot. The glove controller followed a similar design process, but with attention to the circuit design, as this is where the finger tracking system was developed. The next stage was to design the robot vehicle and the corresponding glove controller. The robotic vehicle was designed to carry the weight of the robotic manipulator and to be able to move forwards, backwards, clockwise, and anti-clockwise. The glove controller design incorporates the use of motion tracking to control the vehicle using hand gestures. The use of 3D printing presented several benefits to the research project. The overall weight of the robot was reduced thanks to the lighter weight of the PLA 3D print filament material. The 3D printer that you can see on the bottom left side of the screen is the Raise 3D Pro 2. There are 4 key circuits which are presented as figures A, B, C, and D. And for each circuit that was developed, there's a computer-aided design version on the left side, as well as the real-world implementation on the right side. All circuits were designed using the Arduino platform for ease of compatibility. If I could please draw your attention to figures A and D, these are the circuit designs for the glove controllers for the robotic manipulator and vehicle, respectively. The Arduino Nano microcontroller is used here because the circuits are required to be implemented into gloves worn by the user, and therefore the smaller form factor is preferred. These circuits include the use of flex sensors and MPU accelerometer components for finger tracking and motion tracking. Figures B and C are the circuits for the robotic manipulator and vehicle. The base of the manipulator uses a high torque stepper motor, and the joints of the robot are controlled with servo motors. The servo motors and stepper motor require corresponding motor driver components, and the communication between the manipulator and glove controller uses Bluetooth transceivers, and the vehicle uses radio modules for enhanced line of sight range. The complete system shows the manipulator mounted onto the vehicle, which allows mobility. This greatly expands the potential for industrial applications as the base of the robot can move to different positions. The glove controllers are worn simultaneously by the user, which allows for a natural and more familiar interface to controlling the overall system. This increases the level of human-robot interaction. The code functions using a controller/worker configuration, where the glove controllers are the controllers and the robot systems are the workers. Therefore, when a gesture action is executed by the user, it is detected and the signal is sent from the controller Arduino on the glove to the worker Arduino on the robot. To reduce the likelihood of problems such as incorrect detection of gestures and latency, the system operates under the protocol of only one gesture action at a time. If I could please bring your attention to the right side of the screen where you can see the gesture mapping table. The gesture map is where all the recognized gestures are defined. When a gesture action is executed by the user, it is detected using the finger tracking and motion tracking technology and is defined in the form of a character variable. For example, if the user was to bend their finger to open the gripper, the gesture is recognized by the controller. The lowercase f character is then sent via Bluetooth transmission to the worker Arduino on the robot, which reads the incoming data stream, and once the lowercase f character is detected, the gripper servo motor spins and the gripper opens. Finger tracking was implemented using flex sensors, which cover the index, middle, and pinky fingers of the right hand. As the user bends their finger, the resistance across the flex sensor increases. As it bends beyond a defined threshold, a gesture is detected. Motion tracking uses the MPU gyroscope and accelerometer module. This component detects variations in motion across the X, Y, and Z axes relative to the initial position of the glove controller. As the user bends their wrist, the variation in motion across the 3 planes is detected and the gesture command is executed. This leads nicely to the next slide, which goes into further detail about how the motion tracking system operates using Euler angle calculations. Euler angles are a set of 3 angles that describe the orientation of an object in 3-dimensional space. The angles are typically denoted as roll, pitch, and yaw, which correspond to rotations around the X, Y, and Z axes. These angles are calculated using the data obtained from the MPU module. The MPU combines a 3-axis accelerometer and a 3-axis gyroscope, which allows it to measure both linear acceleration and angular velocity. By integrating the angular velocity values over time, you can obtain the current orientation of the MPU in terms of Euler angles. To determine the direction to move the vehicle based on the Euler angles, a reference coordinate system for the robot's movement is defined. The robot's forward direction aligns with the positive x-axis, the left direction with the positive y-axis, and the up direction with the positive z-axis. Using the Euler angles, the robot's current orientation is determined relative to the reference coordinate system. The roll angle gives information about the tilt of the robot along the lateral axis. If the roll angle is non-zero, it indicates that the robot is tilted to one side. And then based on the sign and magnitude of the roll angle, the required correction to bring the robot back to a level position is determined. The testing involved 3 stages, which include the calibration of motors, the functionality testing of the circuits, and the performance testing of the overall system. The calibration testing was performed to ensure that the motors were set to the correct angles. This made sure that there's no possibility of jamming in the manipulator. Functionality testing validated the flex sensor components used for finger tracking. They were tested to determine the relationship between bend angle and resistance. As you can see on the slide, as the bend angle increases, the resistance increases. Performance testing validated the robot's ability to replicate industrial-style pick-and-place tasks, moving an object from position A to position B using gesture control. Overall, the testing validated that gesture control using finger tracking and motion tracking implemented on glove controllers is a viable method for controlling robot systems. I hope this presentation has demonstrated that gesture-controlled robotics offers a promising avenue for expanding the scope of human-robot interaction. It's really exciting to see the significant potential for use in a range of industrial applications. Thank you very much for listening, and I'll happily answer any questions.
Thanks for your presentation. Dear participants, do you have any question about this paper? Okay, no questions. Thank you again.
Thank you very much.
The next paper belongs to dear Faruk Ünker.
Yes, I am here.
Okay, if you are ready, you can start your presentation.
Okay. Can you see my presentation?
Yes,
Okay. Good afternoon, dear
you have
colleagues.
10 minutes, okay?
Okay, thank you. Welcome to this online presentation. I will present my study titled Recurrent Stabilization of Two-Wheeled Robot through the Control Moment Gyro, or CMG. Okay. And the shock and vibration of a firing weapon have been increasingly studied by researchers. The desire for building weapons with a high as possible accuracy is very essential. The high amplitude of the vibration induced by the increased fire power of a weapon has a significant impact on the firing accuracy. Although an automatic weapon can fire main projectiles to improve the hit probability of their target, conventional recoil absorbers of the most weapon system cannot satisfy the demand of a weapon station. The existing conventional hydraulic recoil absorbers can only control a certain vibration motion, and using a more powerful weapon without a convenient absorber change cannot trace and adjust the recoil process, which leads to weak accuracy of the weapon station. Besides, similar space is available for the conventional hydraulic recoil dampers, which are generally very heavy and big, which significantly influence the probability of a weapon. With their with their lightweight, stable motion, rapid response, and high maneuverability, the two-wheeled robot using gyroscope can meet the higher performance requirements of the armored vehicles. In this study, feedback control associated with the oscillation motion has been shown to reduce recoil, the force, the control label, and the variable angular momentum of a gyro is expected to reduce vibration due to recoil energy, so that heavier weapons. To ignore the compromise between recoil force and wheel, strong gyroscope can be used with closed loop controllers. The Gimbals control torque estimation of the gyroscope can be derived from linear equation motion related to weapons recoil force. In the following research, the theory of Lagrange procedures and the effect due to projectile firing recoil force, as well as the simulation of the robot with the gyroscope, have been described. The system instructions in this study to two-wheeled robot considered for this study includes gyroscope for controlling the reaction force that are caused by firing weapon, as shown in figure 1. In this example, it's supposed that the two-wheeled robot includes to the weapon gimbals, flywheels, and other parts of gyros which are fixed to the two-wheeled robot. The main part of control moment gyro, or CMG, is the flywheel, the overhead cannon or weapon turret. The two-wheeled robot mainly relies on the CMG stabilizer to absorb the energy when the weapon recoils. At the moment of the firing, the angular momentum accelerates the gimbal position. Synchronized gimbal's motion come up during firing. The impact causes the gimbal up to oscillate during firing. The latter feedback controller, or active vibrating controller, is mainly involved in controlling the gimbal of the gyro and wheels of the robot, as shown in figure 3. In figure 3, this the controller. The impact, the theoretical results show that the CMG recoil absorber could effectively eliminate the recoil energy and will suit the robot by using real-time feedback controller. The physical values and description of the robot are given in table 1. Yes. And equation of motion, the flywheel spinning in the constant speed compensates for the curve force by possessing theta. The kinetic energy of the simpler model of the soldier robot with two flywheel gyroscopes and cannon can be written in parts as follows respectively. Then the total energies of the kinetic and potential can be defined as follows respectively for this soldier robot. The soldier robot can be predetermined to have 3 freedom degrees. Then 3 differential equations can be defined in form of 3 unknown zeta, theta, z, theta, and phi of motion. Therefore, the Lagrange equation can be applied to the energy equation of the robot as follows. Then, from this Lagrange equations, the non-equation function equations using Lagrange motion can be derived as follows. And for optimum parameters, we use some suppositions. CMG has been optimized using some assumptions validated through the sinusoidal motions. Besides the angular momentum distribution of that impulse over time or moment during weapon system firing can also influence the wheel movement. Then suppose that the harmonic function should be chosen as angular frequency to balance the robot due to recoil force. The optimum relations for the calculation of the influence of the vibrations on the firing stability of the robot can be derived from 2 cases of sinusoidal assumed sinusoidal motions as follows. Hence, the proportional control gain coefficient corresponding to the flywheel speed omega required for the allowable gimbal amplitude theta 0 and the desired amplitude of the robot's translation motion z0 can be obtained from this equation. A small translation amplitude zeta 0 is desired as possible with a low flywheel speed to shoot a target. Then results for before this results in the calculation and MATLAB tool involving the numerical method for order rubric can be used to solve Lagrange equation motion. The numerical parameters of the solution are seen in table 1 to identify the physical behavior. Non-linear time responses were solved with 0 initial condition and the step size of 0.005 seconds. The force acting on the robot with a certain magnitude and duration can be replaced by the half sinus impact loss for the chosen period of recoil force, which is comparable to real impulsive loss. Valier's formula may be used to determine the magnitude and duration of a recoil impulse based on the internal ballistic theory. The recoil frequency was set according to the continuous firing load of 600 rounds per minute as the actual rate of the fire condition of a weapon, as can be seen in figure 4. The time duration has been shown in figure 4 with 10 continuous firing load pulses presented in figure 4a. With the above defined assumptions, the pulse terrain waveform have been obtained by using only the first 500 harmonics. The average force can be calculated from pulse area, which is equal to the area between pulses, which is approximately equal to 120 newtons. The time response of the theoretical recoil and recoil displacements for alpha 0 and 30 degree are given in figures 5 and 6, respectively. 5 and 6. It can be concluded from the comparison results exposed to recoil force in figure 4 that the tendencies match well with the recoil line once from the beginning of 5 with the optimum K gain K for omega 4,000 radian per second. Meanwhile, the stability performance of the gyroscope is not significantly changed due to approximate momentum of recoil impulsive force, while impulsive force increases, which means higher momentum and amplitudes in the horizontal axis. The stability can decrease without going in control parameters change as a result. Yes, for 30 degrees. Conclusion in this study, as the control moment gyro was designed to control the recoil dynamics of vehicle for the angular momentum concerning recoil energy was introduced. Here, the recoil energy mitigation performance using CMG for two-wheeled robots under both a step recoil force and weapon-based impulsive recoil force has been investigated. The relationship between the recoil force and CMG and the robot in the weapon performance is well defined. In the future, CMG can be an ideal impact damper in weapon engineering. CMG and control moment gyro is smart recoil mitigation device for a larger caliber weapons and may increase the vehicle's stability under weapon fire. Especially, control moment gyro has reversibly controllable torque from the two-wheeled robots to weapons when they expose the recoil force in the milliseconds, giving the control moment gyro a broad field of application. Thank you for participation. If you have any question, you may ask. Thank you.
Thanks for your presentation. Dear participant, do you have any question about this study? Okay, no questions. Thank you again, dear Farfine Hünker.
You're welcome. Thank you.
Next paper belong to dear Jetnipat Tongprasit.
Yes,
Are you ready to present?
yes. Let me share the screen.
Okay, please. You have 10 minutes.
I cannot share the screen because
Okay. Okay,
Okay.
now you can share.
Okay, can you see my slide?
Yes,
Okay,
you
let's
have
get
10
started.
minutes, please.
Oh, yes, sure. Let's get started. Hello, everyone. Jetnipat Tongprasit is my name. Today, I would like to talk about our paper, portioning algorithm using the bisection method for slicing food. Let's start with the outline that I'm going to talk about today. And starting with a short introduction about food portioning and hardware we are using, and then we will focus on the algorithm part for generating cutting planes, and followed by our experiment and conclusion. Introduction: food is essential for us to stay healthy and have energy. In industrial like processing and packaging, it's really important to partition the ingredient equally. This helps make things efficient and reduce waste. However, traditional method can be time-consuming and prone to errors. This has led to a growing interest in atomic food portioning method using technology like machine vision, water jet cutting, and robot and smart knife. And in our study, we aim to develop an algorithm for accurately partitioning material into equal size. Okay, now let's move on to the next slide to explore the system diagram. The first part of the diagram is the hardware. We're using the interior same depth camera, the 435i, to capture point cloud data of the object. And then in the second part, this point cloud data will be processed using Python code running on Raspberry Pi 4 to generate cutting plane position. And actually, it is not, and it is unnecessary to use a Raspberry Pi for controlling the interior sense depth camera and running Python code. And any other microcomputer or notebook can also be used for this purpose. However, the Raspberry Pi was selected for its easy for expansion for future applications. In our setup, we install the camera on top of object and capture the top view image of the object. The object was placed within the frame as shown in the right-hand side picture. And we mount the camera and Raspberry Pi on the AI robot to test their collaboration. And however, this robot collaboration will not describe in this paper. The process of calculating the volume of an object is divided into two parts. The first part, we propose the method to acquire point cloud from interior sense depth camera using Python language and essential library, including PyRealSense2, PinCloud, and Matplotlib. And after running the Python script, we will get point cloud of object as in the picture. And the second part, we using the PinCloud library and its convex Hall function for volume calculation of a point cloud. We use the convex Hall function to create a convex Hall mesh from the point cloud data. And then the resulting mesh encloses the point cloud is in a convex shape. And to estimate the volume, the convex Hall is further processed by dividing it into tetrahedron using Delaunay triangulation. The tetrahedral volume function in PinCloud is used to calculate the volume of each tetrahedron by summing the volume of all tetrahedrons. In this method, we have only one top view image is used to calculate the volume of an object using point cloud. This causes the depth camera to be unable to capture point cloud for certain shapes. The main factor that prevents the point cloud from being captured is the high inclination of the object surface, which prevents the top view camera from capture all the necessary points. But for this problem, several methods can be used to solve, such as using multiple camera or machine learning. Okay, let's go to the next topic, partitioning algorithm. For generate the cutting plane to partition the volume, we choose to use the bisection method. The bisection method is a simple numerical technique used to find the root of a continuous function. A Python script is written to find the cutting plane from the point cloud we have obtained with the following step. In step 1, the point cloud will select the interval A and B from the first and the last point cloud data in the x-axis. This interval will contain the starting and ending point of the object as shown in the picture. And then in step 2, we calculate the midpoint of A and B. And in step 3, divided the object into two pieces at the midpoint and find the volume of object on the left side. And in step 4, we check the volume on the left side compared to the total volume of the object divided by the specified number of parts. That is the volume of each part that we want. And then we divide it into 3 cases. And we will start with case 2 first. Case 2, the volume of the object on the left side more than the volume of each part that we want. Therefore, this position is not cutting plane position. We repeat step 2, 3, and 4 using interval A and C. We will find midpoint of A and C, and then we find volume of the on the left side, and then we repeat step 4, check the volume. In case 3, the volume of object on the left side less than the volume of each part that we want. This position is not cutting plane position also. Similar to the case 2, we repeat step 2, 3, and 4, but this time we using the interval C and B, find midpoint, find volume of object on the left side, and then repeat check. Okay, next is the case 1. The volume of object on the left side equal to volume of each part that we want. Therefore, this position is cutting plane position. And then if you get the number of parts that you specify, the process is n, but it is not the specified number of parts, repeat step 2, 3, and 4 using interval C and D to find the next cutting plane. For instance, we specify number of parts equal to, so we need only one cutting plane to divide the object as in the above figure. But if the number of parts is specified more than 2 after first cutting plane is obtained, repeat step 2, 3, and 4 using interval after the first cutting plane as the figure below. Okay, this is the result if we specify the number of parts equal 4 parts. And this is the Python script in the section of generate cutting plane position. So let's go to the next topic, experiment. In this section, describe the method used to evaluate the performance of the algorithm in partitioning real objects. The material used for testing is persistent, and since the true volume of the material cannot be determined, we use its weight for comparison instead. And then we have 2 experiments performed to evaluate the impact of object size and number of cutting plane variation. The cutting method used in both experiments is using the partitioning by hand. In first experiment, this is an experiment on the object size variation. 3 size of plasticine weighing 50 grams, 150 grams, and 250 grams were used in this experiment. And we set the number of parts equal 3 pieces. And after manually divided object, the result sample were weighed. The entire process was repeated 3 times for each weight. Finally, the weight value were used to calculate the error. And in the second experiment is the experiment on the number of cutting plane variations. Similar to the first experiment, but we using only the plasticine weighing 150 grams and set the number of parts equal to 3, 4, and 5. The result of experiment on object size variation. The size of the object affects the accuracy of creating cutting plane to partition the object volume. The error value was found to be higher when using 50-gram object compared to the object weighing 150 grams and 250 grams. Result of experiment on the number cutting plane variations. The number of cutting planes affect the accuracy of the cutting plane creation partitioning the object volume. The more cutting planes, the higher the error obtained. Error between 3 parts and 4 parts is not significant, but when we divide it into 5 parts, the error significantly increases. And the primary cause of error in both of experiments is the resolution of point cloud that the camera can collect, which is not precise enough to accurately calculate the cutting plane position. Additionally, in both experiments, the error may have been increased due to manual cutting by human hand, the object material, and the noise of point cloud data obtained from the camera. And let's conclusion of this paper. The partitioning algorithm is capable of generating cutting planes to partitioning the volume of an object into equal size. And regarding the error encountered in both experiments, the primary cause of this error can be attributed to the limitation of the camera and manual cutting method. The algorithm can be effectively applied in the process of cutting food by minimizing the impact of experimental errors by using high-resolution point cloud data and accurate cutting tools. The algorithm can be implemented and displayed via Raspberry Pi 4. Okay, thank you all for listening. It was a pleasure being here today. Any question?
Thanks for your presentation. Dear Pasim, do you have any question about this presentation? Okay, no question.
Thank you.
Thank you again. I
Teşekkürler.
wish you success in your career.
Thank you.
Next paper belongs to dear Jiahepan.
Yeah, hello.
Hello.
Let me
Are
just
you
share
ready,
my
citizens?
screen.
Okay.
Yes.
You
Can you see my
have
screen?
you have 10 minutes, please. Okay. Your screen is appear.
Yep.
Hearing.
Okay. Hi, everyone. So this paper is called Variable Grasp Pose and Commitment for Trajectory Optimization. My name is Jiahe Pan from the University of Melbourne, Australia. And I worked on this project with colleagues Carrie He and Jiaming Ong from Monash University and Dr. Kanzel Koskan from Deakin University, Australia. So in this project, we focus on the idea of robotic grasping in collaborative environments. So, as humans, when we want to, for instance, grab a can of beans from the kitchen benchtop, we naturally make a split-second decision on what's the best way to reach for it and grab it. And this decision here actually involves a number of aspects regarding the task. For instance, are there any collision objects around the target? What's the best angle to grab it considering where my hand currently is? Because people are lazy and want to reach towards the object in a way that requires minimal effort. So then if we want a robot to perform decision-making in a similar way, then we should look at the problem of object grasping as a single problem. And this would involve exploring the different grasp poses for a given target object and aiming to select the best one, where the criterion for the best could be the quality of the arm's reaching trajectory towards the target object. So in this project, we propose an algorithm which aims to optimize both the grasp pose and the arm trajectory towards the grasp. And we introduce two key ideas. So the first one is variable grasp, which quite naturally links to the motivation behind the problem. And the second concept is what we call trajectory commitment, where we change the motion planning horizon, which is essentially the start and goal poses between which motion planning takes place. And we use an optimization-based motion planner called TradOpt, which is embedded in our algorithm as a black box optimizer, where we give it planning queries and it outputs solution trajectories if successful. So here we have the variable grasp pose idea, and the parameterization model which we design uses two parameters. They are S and theta. So theta is the grasp angle from the horizontal, and S represents the position of the center point of the end effector. So if we have a look at the picture down the bottom here, these are side views of end effector grasping a target object, and for different theta values. So the little red dot in the center of the black rectangles actually represents the center position of the end effector. And this is constrained to the arc shown by the purple line. And this arc varies with the choice of theta. And the yellow highlighted area represents the overlapping or the contact region between the grippers and the object sides. So this is another interesting aspect of grasping of objects in general. Often when we hold something, we generally prefer having as much contact as we can with the object. So instead, pinching the object with just two fingers. We reflect this desire for more stable grasps through also the parameterization model, where it's able to consistently produce high overlapping regions, like the ones shown here, between the gripper and the target object for all combinations of theta and S. And also the figure on the right here, which is a top view of parallel grippers grasping a cylinder object, shows that we can also generalize this model to round objects by introducing an approach angle, which is denoted by alpha here. So here are two slightly different grasp poses for the same task. And I guess the more obvious difference here is the grasp angle theta. And here's another pair of slightly more distinct grasp poses where both theta and S varies. And next we have the idea of trajectory commitment. So the basic backbone structure of our algorithm is iterative. And in each iteration, we randomly sample a new grasp pose using the parameterization model, and then use TradOpt to generate a trajectory towards the particular grasp. So here, what's interesting is that for similar grasp poses, or even ones that are not too different, the initial section of their corresponding reaching trajectories could be quite similar too. And so essentially we thought, what if after obtaining a trajectory for some random grasp pose in the first successful iteration, instead of sampling a new grasp and replanning the entire trajectory, we fix or we commit a few waypoints near the start of the trajectory that we just obtained. And then we only replan for the remaining section of the trajectory towards the new sampled grasp. So an immediate advantage of this is that TradOpt runs faster since we're asking you to plan for less waypoints. But then a drawback is that how do we know that, for instance, the waypoints that we just committed, which are part of the optimal reaching trajectory for the current grass pose, how do we know that they are also part of the optimal path towards the next or just the future grass poses in general? So we have two ways to tackle this issue. The first is that we would require a few successful trajectories to be generated for the current horizon from different grass poses. And once we have this, only then we make a commitment step. And we commit from the lowest cost trajectory out of the group. And so in doing so, we are essentially minimizing the risk of committing waypoints that reach towards a suboptimal grasp, which can influence the trajectories generated in all future iterations. So the second idea is where we perform an additional refinement step. So if we take a look at the series of snapshots shown here, labeled 1 to 5. So suppose that the robot starts in the configuration shown in 1, and we tell the robot to grab a certain object like it does in 5. Then the first few iterations, we would plan trajectories from 1 to 5 for various grass poses, and then we make the commitment step. And suppose that we make, we commit waypoints up to the configuration shown in snapshot 2, then in the next few iterations, the horizon changes, and we would then only focus on the sections from 2 to 5, and then repeat the same in terms of sampling new grasps, planning trajectories, and committing more waypoints. So this continues up to a point where the horizon becomes very short. And so committing more waypoints would actually increase the difficulty of generating trajectories to newly sampled grass poses, since there's less flexibility. So here, for each successful trajectory generated, we simply join it to all the committed waypoints and then pass it to DragOpt as initialization for it to refine. So this essentially ensures optimality of the overall solution trajectory, which our algorithm finally returns, and also addresses the previous concern of having a slightly suboptimal trajectory overall due to the committed sections of waypoints coming from different grass poses. So in simulation, we designed 4 different task scenes, as shown in the pictures here, and the top target objects are highlighted. These include shelf and tabletop scenes, and both cubes and cylinders are for objects. So the first 3 scenes have initially constrained poses, where the 4th one actually starts in a pose, which from our experience is quite easy to generate trajectories from. And 4 baseline approaches were implemented and tested to compare with our approach. These include RRT Connect, the fixed goal single iteration baseline, where we manually fix the feasible grass pose and then just run TragOpt once to generate a trajectory. And the other 2 baselines are the variable goal single and multi-iteration approaches, which randomly sample grass poses and run TragOpt for either a single or multiple iterations. We obtained results from 300 trials for each of the approach scene pairs in terms of success rate, trajectory cost, which uses the TragOpt cost definition of squared cumulative joint space displacement, and the planning time. So here, our approach shows higher success rates over the baselines, except for the last scene with the easier initial configuration, where the variable goal multi-iteration baseline performs just as well as our approach. Here it shows that our approach is able to generate lower cost trajectories than the baselines in general, again, except the last scene, where it actually resulted in a higher trajectory cost than all the baselines except RRT Connect. And due to running multiple iterations of TragOpt for different grass poses, both the multi-iteration baseline and our approach resulted in much longer planning times compared to the baselines. In terms of real experiments, we also did 10 trials each for 3 of the approaches. And the bottom right picture here shows the task scene with the target object outlined in red. And here the multi-iteration baseline yielded a similar success rate to our approach. And here it shows that the trajectories generated by our approach has a much lower cost than the ones generated by the baselines. And here the comparison in planning time is mostly consistent with the results we obtained from simulation. So here are videos of our approach and also the multi-iteration baseline generating trajectories for the same task. And the one generated by our method, which is shown on the left, has a lower cost compared to the baseline one. And there is also noticeable qualitative differences between these trajectories. So finally, to conclude, there are limitations in the experimental design of our project, which could be addressed by having more randomization in the task scene, including both object poses and also the initial robot configuration. Overall, the results demonstrate that our algorithm performs more consistently and robustly than various baselines for a series of different task scenes. And for future work, we aim to explore adding the mobile base, which is a feature of mobile manipulators such as the fetch, to the trajectory planning problem as extra degrees of freedom. And from some of our preliminary experiments, this has shown to also impact the quality of the arm trajectories. And therefore, we do think that it is an interesting area which is worth exploring. And thank you for listening.
Thanks for your presentation. Dear participant, do you have any question about this paper? Okay, no questions. Thank you again. I wish you success in your career.
Yeah, thanks.
Dear Umbrape Mayor.
Yeah, I'm going to show the presentation.
Okay. You can start if you want.
Okay. Good afternoon, everybody. My name is Phumrapi Meyer from Chulalongkorn University. I would like to present our paper called Web-based Teleoperation System for Enhanced Precision and Efficiency in Food Industry Applications. The outline. First, we'll talk about the introduction, how our paper is important, the overall system implementation, how we adapt with the plan, the operation, result, discussion about the advantage of the paper, and conclusion. The introduction. As we all know, the food industry plays a vital role in feeding the world's population. However, with the increasing demand for processed food products, there is a need for efficient and precise solutions to meet production requirements. To address this challenge, we have developed a novel teleoperating system specifically designed for food industry. Our system enables remote control and monitoring of food cutting process, eliminating the need for physical presence. By integrating teleoperation with IoT technology, we can ensure real-time communication, data collection, and analysis for improved operational efficiency and quality control. The overall system. Our system consists of the web application interface built using the FAST, our versatile web server framework known for its simplicity and scalability. And for the interface in the web page, there is this, the HTML and JavaScript work together to create an interactive and responsive web application. Then the socket I/O is for communication between the client and the server in real time. To leverage the capability of IoT, we employ the MQTT protocol, a widely accepted standard for communication between the controller and server. The system implementation. The pan, as you can see in the picture, the robot is the Cartesian robot called the IAI tabletop robot, which we use for cutting the object. We attach the sharp metal sheet at the middle of the Z-axis. The robot communication with the controller using a IAI protocol B. The pan controller in this system is powered by a Raspberry Pi 4, which is connected with the robot via serial communication port and connect with the Intel RealSense depth camera for generate the point count and the cutting part. The main server. In this paper, we test the system in the local network. So the main server only need for the Mosquitto MQTT broker and Fax web server. Web client, the website, once the source code for the front end web interface has been created, testing the system requires only a browser that capable with the socket IO feature. Here is the overall of the system. The main server communicates with the Raspberry Pi or the PAN controller by MQTT protocol, and with the main server communicate with the web application by socket IO. And the Fax server used in Raspberry Pi to stream the camera to monitor the whole process. Here is the operation. This code, we have the index HTML is for the client part. This is the structure of the web. And in the blue box is the server part, and the orange box for the PAN controller. The PAN controller is adapt, but the PAN controller is from the design of the robot application for slicing food into equal volume equal mass slice. Here is the flow of the command. After we submit the number we need for cutting, it will emit the event to the main server, and then the main server will publish the number to the PAN controller, and then after we click the start button, it will emit the start command and publish the MQTT to Raspberry Pi and phone like this. Okay, here is the result of the web application. We can see the whole operation and see the 3D graph of point count data and the cutting part that generate, and when it operation, and when it operating, you will see that it's cutting and the position of the axis in real time. Okay, here is a Dropbox page that we save the image, the PAN output, the image folder and the text folder. Here is a video. We input the number and submit, and then we click start process. Okay, in this discussion, we talk about the advantage of this system. The teleoperating system implemented in Python offer numerous benefits for the food industry, specifically for cutting food into equal volume. Python extensive ecosystem of tools and libraries enhance the server capability, allowing the efficient, the tailored development. Integration with image processing library enable precise measurement and calculation for achieving equal volume cut. The web interface provides accessible control and monitoring from any device with a web browser. Integration with Internet of Things ecosystem to MQTT allow for connecting and interacting with various devices and optimize cutting parameters. The system can be adapted to incorporate a digital twin concept, providing real-time visualization, analysis, and optimization of the cutting process. Dropbox is utilized for scalable data storage, allowing in-depth analysis and evaluation of the cutting process. Deploying the web server using a PaaS provider simplify the development process, and port forwarding enhance external network access for the camera feed. In conclusion, the system effectively control the pan and present real-time graph, image, and video and text output. MQTT protocol enable communication and compatibility with MQTT enable controller in various pans. Flask server facilitate camera streaming and serve as the main server alongside the MQTT broker. User can effortlessly access the web interface using a standard web browser. The Dropbox API is utilized for storage of generated data throughout the process. The system can combine teleoperating capability, IoT technology, and cloud storage. In the food industry, the system enables consistent precision, improved efficiency, remote operation, real-time communication, and valuable data gathering. The system ensures scalability for future growth and enhancement. Thank you for your attention.
Thanks for your presentation. Dear participants, do you have any question about this presentation? Okay, no question. Thank you again. I wish you success in your career, dear Comprameyer. Next paper belong to dear Boom Separatananan.
Yes, I'm here.
Okay, if you are ready, you can start your presentation.
Okay. Good afternoon, everyone. My name is Phumse Parathanan. I'm from Faculty of Engineering, Chulalongkorn University. Today, I'm going to present about topics design of the robot applications for sliding foods into e-commerce life. Let's begin with introductions. In the future, robots are going to become significant, more important for human daily lives. Robots are used to do various objects across many industrial, especially in the food industrial. For example, the slide of the chicken breast. The objective of this paper are to design and develop the robotic applications to control the robots for slicing chicken breast into e-commerce slides perpendicular to the x-axis or 1D dimensions cuttings and estimate the errors of each slide pass. In these papers, we apply the AI robots and interiors and depth camera that's shown in this right side figure. Next, I would like to talk about the kinematics of the robots that consists of reverse kinematics and inverse kinematics. In these papers, we derive both kinematics based on data with conventions. This consists of 4 parameters: link length, link width, link offsets, and a joint angles. These are denoted by A, alpha, D, and theta. The non-determinable parameter of the IAI robots can be listed in the table 1 and visualized in terms of the reference frames diagram in the figure 1. Independent variables of the link offsets, either D1, D2, DT, is also called a joint space variable and can be expressed in terms of the QI is member of the 3-dimensional real space. It's importantly to derive the data with Vandenberg parameters are used to specify the homogeneous transform matrix. This can be expressed in terms of transformation tree that consists of the rotation metric R and the position vector P's that can be expressed in the right size equations. Next, apply the metric kinemation, apply the transformations to derive the forward kinematic and inverse kinematics. Then the forward kinematics is used to determine the position and orientations of the reference frame attached to the effectors of the robots. On the other hand, the inverse kinematic is essential to derive the set of choice variables that achieve to deserve and effectors configurations of the robots that can be expressed in these equations and equations. Next, we talk about just robotic applications. As mentioned in the objective of these projects, in these sections, we described about robotic applications for controlling the robot to sliding foods material into portion of equal mass slice. The robotic application described in these papers consist of 4 procedures. Firstly, settings of operation system. We apply AI robots and intelligence step camera that's shown in figure 2 and figure 3. As mentioned in the figure 2, the homogeneous transform matrix from the reference frame of the origins and home configurations of the IAI to the global origin can be defined in these 2 equations. And in actually operations, each joint of the robots have the limitations on its move. Thus, the limitations of the joint variable space is defined in these equations Q. Next, the depth camera is hold on the upper parts of the IAI robots. When the robot moves, the camera also moves. Interpret that the configurations of the camera is related to the end effectors that can be expressed in transformation tree from the camera to the origins. For the point cloud captures in the next procedures, we need to move the robot to the home configurations of the IAI. Moving the robot to home configuration requires the input of joint variable space related to the origins of the IAI robots that can be derived by using transformation mapping in these equations and expressed in terms of joint variable of the home configuration in these equations. Next procedures is the point cloud captures and transformations. Each pixel of the pictures which can be captured from this camera have a data about object depth in terms of the Cartesian coordinate system X, Y, and Z, and expressed in terms of the position metric P for objects to the camera. However, its position metric is related to the camera positions and orientations, and is essential to transform it into positions related to the global origin frame to calculate, and can be derived by using these transformations and this transformation tree from the camera to the origins. Importantly, in actual operation, it's necessary to designate the operation systems related to global origins, and also called as O space. The O space can be defined in these equations and can be visualized in the figure 3. Observe that O space boundary is analogous to the cube. Next, solid slice algorithms to divide this solid S into the M equals line perpendicular to the x-axis can be written in terms of equation. In this equation V, where M is number of divided solids and V is the volume of each equal slice. First of all, let X be generous partitions of the interval XA to XB, also called as vector of cutting plane line. In this papers, we developed the algorithm to find the cutting plane line vectors. Following these algorithms by step 1 through step 6. The answers from this algorithm is a set of the vector of cutting plane line that is used to the next procedures. And final procedures is the robot operations. The homogeneous transform matrix from reference frame of afters and lower configuration can be expressed in these 2 equations. And in this operation, we start in the flowchart and following the flowchart is shown in figure 5. When the robots move to lower and upper configuration following flowcharts, the solids are slide perpendicular to the x-axis by sliding pads that hold on to the end effectors of the robot. Next is illustrated examples. In these figures is an example to the cuttings by this robot into the 3 equal mass line. Next section is the experiments. The objective of this experiment is to evaluate the errors of each slice perpendicular to the x-axis. The material that is used to make the objects which represents the chicken breast is, in this experiment, is hydroponic sands, and the object's weight is 100 grams is placed on the old space, can show in figure 3. In this experiment, we follow the procedures of the robotic applications. One, set the operation system and captures and transformations the point cloud of the objects. And two, slide and objects into 2, 3, and 4 parts. Next, 3, the entry process is repeated 5 times for each pass. And lastly, the weight value that are collected in these experiments are used to calculate the error. The results of this experiment can be listed in table 2. From the table 2, observes that average error increase following number of deserved slide. And in terms of discussions, the errors of each slide is affected by several factors. For example, resolutions of the point count and mistake of the robots. In terms of conclusions, these researchers can design and develop the procedures of the robotic applications to control the robot for sliding chicken breast according to the objective of these papers. And performance of robotics applications can be expressed in terms of the errors in the previous sections. And lastly, to improve the robotic applications in the futures, we apply the observers and estimator to reduce the errors of the robot's movements, or test the robotics applications with various type and material of the objects, and finally apply the web applications to operate the system on the website. Thank you for your attention.
Thanks for your presentation. Dear participants, do you have any question about this study? Okay, no question. Thank you again, dear Separat.
Thank you.
The last paper belongs to dear Sarah Woodlin.
Yes, yeah.
Okay, are you ready to present?
Yeah, I'm ready.
You can start your presentation.
Hello, everyone.
You have 10 minutes, please.
Okay. Hello, everyone. My name is Laudlin. Today, I'm going to introduce our research about the unknown input non-linear observer for a soft pneumatic robotic gripper application. Due to the complex dynamic of a soft pneumatic gripper, it can be difficult to accurately control the gripper behavior. So one solution to address this challenge is to use an unknown input non-linear observer, or UIO, which is a type of control strategy that can estimate the unknown input of the system, which is the gripper deformation based on the available measurement. To implement the UIO for a soft pneumatic gripper require an understanding of the system dynamic and the mathematical model of the system. So methodology of this system divided into the 3 main parts, which is the system dynamic of soft pneumatic gripper, mathematical model, and the unknown input non-linear observer. Firstly, explain the system dynamic. From the right figure, which is the system schematic diagram, the ambient air was pumped into the air tank by air compressor. Then the pressure of the system was controlled by the regulator valve. Next, the air volume in soft gripper system can be in and out or adjusted by the air cylinder, which can be moved by controlled piston that connect to the linear state. And also the linear state was driven by the DC motor with encoder. Finally, the controller board is used to control the both solenoid valve and DC motor. So this system can control the gripper behavior. Secondly, the mathematical model of system divided into 2 parts. The first part is the model of DC motor with encoder and air cylinder. As you can see from the first row of this model, is the dynamic equation, which based on the Newton's second law and Kirchhoff voltage law. And the second row is the dynamic model of rotor, which had a reaction force from the air cylinder. That's caused by the pressure pushback force in the form of mu1. And last row is the equation of piston position, which wrote in the form of motor angular position or theta. The second part is mathematical model of soft gripper, which can model as an air cylinder attached with a spring and damper, and then generate the model using a free body diagram, which also have the pressure pushback force in the form of like mu2. And for this system, only angular position of the motor theta can be measured. So the measurement equation is divided by the equation below. And moreover, all of the parameters assumed to be known, and the UIO will be implemented to estimate the deformation of the soft gripper. Next, explain the theory of unknown input nonlinear observer. This slide presents a methodology for designing observer that mu are the unknown input. So the objective of this method is to estimate this unknown input mu, and also to estimate the state vector x. To begin with, in the red box is the dynamic equation of the system, and y is the measurement output, which was differentiated in the number of mu times. After that, the equation of the x dot was substituted into the differential equation, and then solve the equation in the form of mu hat, or equation 20. And as you can see in this form, the derivative of the output y can be known from the measurement, and the filtered derivative from this output are given by the left section below, and the state input vector x can be found by using the nonlinear observer design, which is in the right paragraph. And in the blue blocks is standard nonlinear observation form is to estimate x hat, and the new dynamic equation for this plan, which is equation 22, came from substituted the estimated unknown input equation 20 into the dynamic equation, and after that rearrange the equation into the standard form. So the state vector x can be estimated, and now all the parameters in equation 20 unknown lead to the unknown input mu can be estimated too. So here is the observer design for pneumatic gripper system. From the mathematical model of the system, given the A, B, C metric, and given the last parameter, which is a non-linear function, and then substituted into the estimation unknown input equation mu hat. From this equation, the derivative of output y can be known by measuring the output, and the state vector x can be estimated by using a nonlinear observer design method. So mu1 is known and substituted into the equation from the mathematical model, and lead to the estimation of gripper deformation or position x2. This is the simulation of the system. All the known parameter, which is motor and ball screw parameter, air cylinder parameter, and gripper parameter were assumed. So using MATLAB to be implement this system, and the motor position is controlled by PID controller. Lastly, the observer gain found by using the standard observer. So this is the data result from the simulation. It shows the unknown input, which is mu1 and x2, and all the state parameter of the system in the right graph. It can be seen that our estimation quickly converted from initial value to the corrected actual value. So these estimated parameters are very useful to control the gripper behavior. And now the volume in gripper is known because it related to the deformation of gripper X2 that can be estimated. So this control system is designed to control the volume of soft gripper by using MATLAB Simulink and PID control with the state flow, and can prevent any accident and can control the system perfectly. This slide is tuning PID parameter for system. The graph shows the response of soft gripper in different PID parameter and choose the best response in off gripper, which is the red line. This test was decided to test the ability to feed a desired air volume into the gripper with various initial pressure value. The test was done by feeding initial pressure into the system. Then the motor activated to feed air into the gripper until its volume reached the desired value. And according to the graph, the desired volume was set to the 33 ml, and the system could feed air into the gripper to reach this volume. And the results show that the plant could deliver accurate result when feed a proper initial pressure into the system. So this control system can deliver a good result. It can feed air into the gripper until the desired volume is reached and able to suck air out from the gripper to decrease its volume. And to conclude, due to the good result of volume control system, it seems that the estimation of gripper deformation or position by using the unknown input nonlinear observer can be applied. Thank you.
We can't hear you.
Sorry,
We can't hear you.
really?
Your presentation is over.
Yeah. You
Okay.
didn't hear me for like
Okay.
at the start.
Dear participant, do you have any question about this paper? Okay, no question. Thank you again. I wish you success in your career. Dear participants, thank you for your attending. I wish all participants continue success. The session is over. You can your symposium certificate download our web page. See Zoom chat panel. Okay. Participation certificates of the participants who made their presentation can be downloaded from the system electronically. You can see detail our web page. Okay, I would like to end this session. Have a good day. Good luck. Hope to see you at next sessions.